Previously in maths, we sketched the curve y equals e to the minus x squared and saw that it had a kind of bell sort of shape. We then integrated it just for the fun of it using trapezium rule. Then we saw that actually, hey, it seems to have this application in loads of places in the world. And we saw that it's actually called the normal distribution. And we talked about the history of it. We then even talked about roughly where it came from in terms of a histogram, a relative frequency density plotted to give the probability end of the curve. And if you make the group smaller, it becomes more and more like a continuous curve. And this is what the normal distribution is. It is involving e to the minus x squared. Then if we want to find the probability of some measurements, we actually need to find the area under the curve, which links back in to this trapezium rule from before. We then looked at something called the standard normal distribution, and I said, hey, here it is. And I said, oh, the mean is 0, and the standard deviation, or the variance is 1, or the standard deviation is 1. And I convinced you, I hope, of the mean, and I just asked you to trust me about the standard deviation. I then talked about the fact that this pi comes from somewhere, and it's actually to make the area underneath all total area equal to 1. We then looked at this idea of a cumulative probability distribution, integrating from minus infinity up to z, and we saw that actually we can put it into our calculator, and it gives an answer, this one here, exactly the same as when we use the trapezium rule. So more generally, if we're integrating between two values, we do this, but we can use our normal CD button. We practiced that, we looked at some upper and lower limits, we even looked at an equals where we saw it was equal to 0. And then finally, bonus video, which you may have watched, actually proved that the area underneath this curve here is root pi, and therefore for the standard normal distribution it's root 2 pi, and that's exactly why I have to divide by it here. Okay, let's start this by just recapping. Pause the video, see if you can deal with these 4 questions. So we've got the standard normal distribution. We are using our normal CD button. Actually, I'm just going to show you the answers because if you got them right, you can move on if you're happy with that. Otherwise, I'm going to talk through it. Menu, distribution. We always use the normal CD. Lower limits, -1. Upper limits, 1.5. This is doing a numerical integration of the standard normal distribution. And there we go. And we can round it. If I'm doing less than 0.7, I'm going to make the lower limit something really big. I've used -9999. Some people like to use some standard forms, so maybe 10 to the power of a really big number. Okay, even quicker to write then. 0.7. Your calculator can deal with it. It must do a cutoff at some point because it doesn't seem to take very long. And we get that answer. We can do the same for the other one. I could do an upper limit, so 0.3. And then just make this. I like my 9s. I'm going to stick with them. Here we go. And then if you do choose to put in 0.6 and 0.6, you'll see that you do in fact get 0 because you're not, oh, sorry, should have been 0.65, but it's the same idea because I'm kind of finding not an area, but it's like this infinitesimal little strip. And that is always the case for an equals. Today we're going to look still at the standard normal distribution, but the inverse of it. And what this does is it gives you the value of z if you know the probability that capital Z is less than or equal to z. This is an interesting problem because you've done integrations like this before, but normally you can actually integrate the function, but the actual equation of the normal distribution is not even examinable, so I'm not going to talk about how your calculator actually figured this out. We're just going to roll with it and trust it in this case. So here goes. Here we go. We've got probability that z is less than a is 0.9693. Where's that value of a going to be? Well, I think it actually helps, again, to look at the sketch and think about it. It's going to be up here somewhere. So just gives a bit of a feel. I know it's going to be around 2, you know, maybe it's greater than 2, maybe it's less than 2. What I do is I get my calculator, and instead of doing normal CD, I've got this thing called inverse normal. And this is what it does. It does exactly what I said up there. It returns the value of z when you have the probability, when you have the area. So it's going to be 0.9693. I've got my standard distribution, that's all I need, and it returns the value of A, 1.870. You can give it to 3 sig figs here, that's the first answer. Hopefully you're happy with that. So this can be used from now on whenever you get a probability like that shown. So try question 2 yourselves. For this one, same idea, you can press equals and it'll get back to it. Before I do it, I can see this is a very small amount, so I can see it's going to be negative now, and it's going to be, this is my area, I'm expecting a negative value, maybe close to -2, around that sort of region. And there we have it, -1.41. Next one, okay, because I don't always have the less than, what if I have a greater than? How can I deal with this? Well, there is no sort of function on your calculator that will deal with the greater than, but we can do it ourselves. If the probability is Z is greater than C is 0.3821, then we can do the probability that Z is less than C by doing 1 minus that amount. 0.6179, sorted. And now we're back in great territory. It's going to be around here. This is my value of C, and I can chuck that into my calculator. Isn't this good? So 0.300, I suppose. And I'm pretty sure that was a mistake, that 1.87. Let's go with the one I just said, 0.30. Because that was the same that I had before, I didn't change it. All right, so we can deal with these. By the way, it's absolutely fine to not put an equal in on either one. Whilst you have to be careful with the binomial distribution, it doesn't matter here. Yeah, actually, this is the same thing. Remember, if you have an equals, then the probability that it's equal to something is 0. So you can just use greater or equal to or greater than as you please. They are the same thing. Try number 4. It's going to be a very similar thing. 1 minus, and then we can see if it's 0.2877, it's going to be negative. It just helps, doesn't it? You kind of expect it to be negative, and that looks about right. Although I did get it wrong before, so I kind of feel like I should just check. Yep, there we go. I mean, I know I've been a bit like, this is to 3 sig figs. This is technically only to 2 sig figs. Like, I'm just illustrating the idea here. You should actually give your answer to 3 sig figs in general and stats. Okay, what about this cheeky little one here? So I've got f plus 0.2 is 0.111. Well, it's going to be over here somewhere. This is my f plus 0.2. But it is the same idea. I'm just going to put 0.1111 in here. And that's my f plus 0.2 actually. So then I just need to minus 0. Okay, I called it e. Why did I call it e? A few little mistakes creeping in here, but like, you get the idea. F plus 0.2 is this minus 1.221, as you can see. So then I just need to minus 0.2 from it. It's a bit like when you solve a trig equation, x plus 30 degrees or whatever. I just need to undo that value as well. Okay, have a go at number 6. Number 6, very similar. But first of all, we need to get it as a less than. So it's going to be less than is 1 minus 0.1. We get 0.9. Get our calculator. 2g minus 0.4 is 1.281. Okay, then you just have to rearrange and solve it. Add 0.4, divide by 2. That's what you get. Forgot to do, I mean, it doesn't really, it's got a bit less meaning here, but it should have been up here. That would have been my 2g minus 0.4. Again, I can see that looks about right. Bit further down. Okay, 2 more. How about this one? Slightly unseen question. I've got D on the right and on the left. Well, let's see if you got it. This was the answer. 1.18. I'm going to talk about it now. Again, I think the diagram, this is why the diagram really helps. I know it's 0.762. Don't know exactly where it is, but let's just put it here and here roughly. Right, now we've got to remember that because this is symmetrical, this little red region is going to equal this little red region. And so the first thing to do is find out that little red region, and that's going to be 1 minus 0.762. The outside region has this probability. But we know that these two regions are exactly the same, and so each one is going to be 0.119. But that there is this, and that's going to be the probability that Z is greater than D. Here's my value of D, here's my value of minus D. So the probability that Z is greater than D is going to be half of this 0.238. I've turned it into an equation we've already seen. The reason I've made it a greater than D rather than less than minus D, I just think the less than minus D is a bit confusing. You'll solve for minus D and then you'll have to rearrange it. You can do that, but I'm going to go with that. And then I'm going to do my normal thing, do 1 minus 0.119, get Z is less than D, and then we're there. Okay, we can just put that in and then we'll get 1.180. Hopefully you're happy with that. Your final one to try is this one, number 8. Okay, here's the answer. If you just want to check it, 0.3416. Going to talk through this one. So this time I got this area of 0.6. It's going to be a bit less than 1.1, I can see. So let's put it here and here. Okay, I'm not going to label it. It's quite a long label, so I'm not going to do that. But what I can see, I've shaded that red, so what I can see is these other two regions, they're going to make up 0.4. And by the way, I should say that minus D plus 0.5 is equal to minus D minus 0.5. So I need to check that it is actually a symmetrical situation going on, a bit like it was before. It's obvious to see it here, D and minus D, but I need to recognize that this is minus what that is. So I can use the symmetry. The blue area is going to be 0.4. It's going to be shared. So each one's going to be 0.2. And I can write down the probability that Z is greater than D plus 0.5. This point here is equal to 0.2. I've turned it back into a question a bit like 5 and 6. Just do 1 minus. Probability that Z is less than D plus 0.5 is going to be 0.8. And then we can solve for D plus 0.5 with our inverse normal function, and we can minus 0.5. Okay, trickiest one so far. I hope you are happy with that. Let's just backtrack a second and look at probabilities again. Sometimes we're interested in how much data lies between the first 25% and the 3/4 amount, and that would be the interquartile range that you'd actually be calculating. Other times, this is a new idea really, but other times we're interested maybe in how much data is within one standard deviation of the mean. So for a general normal distribution, it would be this, and I'd be saying, how much data have I got here? It's giving me a feel for what's going on. So this is what I want you to do for the standard normal distribution. Can you find out how much data lies within one standard deviation of the mean, 2 and 3 standard deviations of the mean? Well, in this case, it's just a probability that Z is between minus 1 and 1. And you can use your normal distribution function for that, and that's what you get. And if you do it quickly for the other ones, minus 2 to 2 and minus 3 to 3, then this is what you get. You might think this is not that spectacular, but actually it turns out that these values are true for any normal distribution. If I'm looking 3 standard deviations of the mean, I get this amount. I get nearly all the data, and that's the key thing. I get almost all the data, even though it goes to 0 as an asymptote, it never actually reaches 0. I pretty much have all the data within 3 standard deviations. So if you're applying it to height, you can be pretty confident that you've got almost everyone within whatever the mean height of the population is. If you can figure out the standard deviation, you've got almost everyone within 3 standard deviations of the mean. For 2 standard deviations, you've got 95%. For 1 standard deviation, you've got about 2/3 of the people. So just like I said, although we've just shown it for the standard normal distribution, it's true in general, and it's something that you need to know. Last question. Calculate the points of inflection of the standard normal distribution. Right, I'm going to take this slowly, I think, because actually I've got a function of a function, so I need to use the chain rule. So the first thing I'm going to do is I'm going to let u equal minus z squared over 2. So f of z, which actually is f of z of u, or f of u of z. I think I need to change it to f of u of z, to be fair. Yeah, I'm not going to write it at all. I'm just going to say that it equals 1 over 2 pi e to the u. So if I want to find out what df by dz is, I can do df by du, du by dz. Chain rule. df by du is just 1 over 2 pi e to the u, and then du by dz, I need to differentiate up here. I'm going to get minus 2z, but then I'm dividing it, sorry, I'm going to get 2z, but then I'm dividing it by 2, so I'll get z again, and then I'm making it minus, so I'm going to get minus z. Maybe I'll write this as minus 1 over 2 pi, get the z in, and then it's going to be e to the minus z squared over 2. That's my first derivative. You might be confident with the chain rule and be able to go straight to that, okay? Because you realize that you just basically, you differentiate this, like bring it down, and then you keep it as it is there. But I wanted to go through it in slightly slower steps. Okay, by the way, do you remember how to find the points of inflection? It's when the second derivative changes sign. So it's when df by dz squared changes from positive to negative or negative to positive. Maybe you're wondering why I was finding the first derivative, but we got a bit more to do. We need to find the second derivative. d2f by dz squared. Right, now I'm going to need to use the product rule. So I think I'm going to treat this as u and the rest of it as v. Oh, I can't take it out, but the rest of it is v. Actually, not the minus bit. Let me rewrite it. So I'm going to rewrite it as minus z times 1 over root 2 pi e to the minus z squared over 2. This is going to be my u, and this is going to be my v. The reason I'm going to call this v is I've already differentiated it. I already know the answer. It's this whole thing here. So d2f by dz squared is going to be u prime v plus uv prime, or vice versa, and u prime is going to be minus 1. It's going to be minus 1 times 1 over root 2 pi e to the minus z squared over 2 plus minus z times this thing differentiated, which I've already done. Here it is, this thing here. So it's minus z times minus 1 over root 2 pi z, and then e to the minus all that other stuff. Sorry, I ran out of room. Gonna keep going. Not looking very nice, is it? Maybe you think it is. I think it's worth doing two things. I'm going to factorize out. No, I'm not. I'm just gonna kind of rewrite it. So it's going to become z. I'm going to deal with the second term. It's going to become z squared 1 over root 2 pi e to the minus z squared over 2 minus 1 over root 2 pi e to the minus z squared over 2. So I need to work out when this is greater than 0 and when it's less than 0. Now sometimes, I don't know how you've been taught like finding the point of inflection, but you shouldn't really ever set the second derivative equal to 0, because there are times when you get a point of inflection, but actually the gradient, the second derivative at the points is a bit of an issue, such as if I get a curve that looks like this, then actually the first derivative doesn't exist at this point because it's infinite. But I can see that the function, the gradient is increasing and then it's decreasing. So there is a change of sign. So I'm gonna do it how I think is the proper way. I'm gonna solve when it's greater than 0 and then when it's less than 0. And I'll probably get away with it in this case. So greater than 0 when, and what I can do now, and it's absolutely fine to do this, I can just basically divide through by this thing, because this is never 0, and this, yeah, these together are never 0. And I can also divide through by the constants. So it's going to be when z squared minus 1 is greater than 0. And that's going to give me z plus 1, z minus 1 greater than 0. And my quadratic is going to look as such. It's going to be, I've got a thing at minus 1, I've got one at 1. Where is it greater than 0? Z is less than minus 1, or Z is greater than 1. I can actually see in this case that I would get away with setting it equal to 0, but I'm still going to go through with it. So less than 0, it would be the same process when z squared minus 1 is less than 0, and that's going to give me this region here. It's going to be minus 1 less than z less than 1. But where is it changing sign then? Well, it's you can actually see it is at the values. It's going to be at minus 1 that it changes sign, and at 1. So the points of inflection are when z equals minus 1 point of inflection, or 1. To be honest, I'm just interested in the z values. You could substitute this back in and get the value of f of z. It's just going to end up involving 2 pi and everything. But I just wanted to make this point. That's what the point of inflection is. Why do I care? Because look at it. For the standard normal distribution, it's actually the standard deviation and minus the standard deviation. I wanted us to prove that was true, but guess what? Again, it's true in general. So to summarize what we've just done, okay, we've just kind of taken a little detour. We've only proven it for the standard normal distribution, but here's the facts. And this is what it says on the specification for OCR for this statistics module. You learners should know and be able to use the facts that in a normal distribution, about 2/3 of the value lie in the range mu plus or minus sigma. That's one standard deviation of the mean. About 95% within 2 standard deviations. Almost all values, that's that 99.7% within 3 standard deviations. And the points of inflection occur at mu plus or minus sigma. Now we've only shown it for the standard normal distribution, but if this is mu and then sigma, I don't know if sigma's here or what I've got. Well, I know I've got 2/3 of my data, so that does seem about right. Minus sigma, okay, 2/3 of my data here. Then here and what's it's meant to line up here and here, there or thereabouts are my points of inflection. If we just take a look at it, look, we can see the gradients increasing, and then it starts decreasing, and then it starts increasing again, becomes less negative. So just to end today, I hope you're happy with that. We've proved it for the standard normal, but you need to be aware that it's true in general.